Okay. Okay. So, yeah, the question, does this matrix multiplication make sense? This particular one? Yes, no, maybe.
Yes.
Okay. So if it kind of makes sense, then exactly the same way we get, um, you know, this matrix and then the sum over K here. So we can write this Hamiltonian um, uh, H equals A dagger B K and then a matrix here. Let's call it H of K and AK BK sum over K. So this is a 2 by 2 matrix. H of K is EA minus T 1 plus e to the power minus IKL minus T 1 plus e to the power IKL and AB. So that's our Hamiltonian in K space. Just that middle part for the kth moment, kth wave vector or momentum. And how do we get the bands? Now it's kind of simple. We have a matrix, 2 by 2 matrix. If we diagonalize this, find the eigenvalues, then those will be our bands. Okay. So if we diagonalize, we get the bands EK equals epsilon A plus epsilon B. Yeah, you need to try this on your own, like trying to diagonalize this. You can use any Mathematica or math software. EA minus EB by 2 whole squared plus T squared 1 plus e to the power IKL. Uh, uh, and whole square and a square root. So it looks like a constant, say epsilon A plus epsilon B over 2 plus minus epsilon A minus epsilon B over 2 whole square plus T squared 4 cosine squared Ka over 2, right? So we have two bands, and so we can call it two eigenvalues, E plus and E minus of K. Okay, if we plot these, the graph would look like this. For E plus, it's like this, and for E minus, it's like this. Okay, so there you go. We have this will be the conduction band, and the E minus will be the valence band. Okay, so from this tight binding model, you get two bands. One is conduction band, another one is valence band. Now, we also have EA and EB. Remember, these are constant shifts. This is also a shift, but the actual feature comes from cosine square K over 2. And this plus minus sign is important. If you consider EA and EB to be 0, right, then EK would be plus minus square root of 4t squared cosine squared Ka over 2, right? So that's how we get the sign flip. This is like cosine, and if you multiply by minus 1, we get the valence band. Okay. Does this idea make sense, like using A and A dagger operator to get the bands? This idea is kind of the same in many models. Okay. Questions? Okay. So what happens in topological insulator is the same tight binding model, except what is it? You know, uh, this condition T1 is not equal to T2. That's the only condition. So instead of uh, putting T for both interactions, we put T1 and T2, and the Hamiltonian, which is called the um, SSH model, or Su-Schrieffer and Heger or Heger, I don't know how to pronounce that, model. And here T1 is not equal to T2. Okay, that's it basically. So if you look at the Hamiltonian, this one, and we assume EA equals 0 equals EB, because that only creates constant shifts, right? And h of k for that case would be 0, T1 plus T2 to the power minus IKL, T1 plus T2 to the power IKL, and 0. That's it. T1 not equals T2. Okay, that's the Hamiltonian for SSH model. And the bands are like this, T1 squared plus T2 squared plus 2 T1 T2 cosine Ka. And you have plus minus. Okay. And there are many properties of this Hamiltonian. For example, it's invariant under time reversal. And for this particular model, if T1 is greater than T2, that's called the trivial phase. And if T1 is less than T2, it's called the topological phase. Okay. And uh, uh, you know in topological phase, let me share my other screen and try to show you the bands, and like why is it the phase that is called. So stop share, and here I can uh, uh, where this what uh, can I share my screen? Yeah. Okay. Yeah. Can you see my screen?
Yes, it's visible.
Okay. So not this one. Okay. So okay, that's the SSH Hamiltonian. In K space, just the two off-diagonal components, and that's the eigenvalue. And this is the trivial phase, this is the topological phase, depending on which one is greater. If T1 is greater than T2, we get the trivial phase where intracell hopping dominates. So if you remember the diagram, oh, I didn't draw that diagram here. I need to. So T1, you see, in the Hamiltonian, if you consider the T1, that's in the same cell N, right? Between A and B of the same cell. And T2 is between cell N and N plus 1. That's T2. So when T1 is greater, meaning interaction between atoms on the same cell is greater than interaction between the cells, then we get the trivial phase. And when it's the opposite, we get the topological phase. And then I have written the code and that generated this graph. Okay, so we get the bands as before, conduction band and valence band. And we also get something called the winding number. Now, what it is, um, that, off diagonal terms, we call it dk, and it is a real and imaginary component, right? Because it's just T1 plus T2 e to the power IKA, real and imaginary component. And real component is T1 plus T2 cosine Ka or cosine Kl. This is the lattice constant of the separation between, inner size of the inner cell. And imaginary component is T2 sine Ka. And when we plot that, um, imaginary component along y-axis, real component along x, we get a circle. And the origin of the coordinate system, see, 0 point lies inside the circle. Okay, and that's the topological phase. All right, and we keep, you see, T1 here is 0.5, T2 is 0.1. So T1 is smaller, topological phase. And when they're equal, these two bands, they come closer, and then like the band gap closes here at T1 equals T2. And that origin of the coordinate system 0, 0 is on the boundary of that circle. And if we keep going, T1 is greater and T2 is smaller, we again see there's a band gap, but this time that origin is outside the circle. So that's the trivial phase. And this is the point where we have the transition, gapless. This is the gapless state or the transition state. Okay. So that's kind of what's going on underneath. And in topological phase, some properties remains invariant. And yeah, in topological phase, winding number like nu is 1. What is the winding number? Like idea is the origin of the coordinate system, how many times the circle goes around the origin of the coordinate system. In topological phase, 1 time. In trivial phase, none, because that's outside the circle. The circle goes around, but it never goes around the origin of the coordinate system. Now, you might ask, why is a circle, not ellipse? Good question. The reason is when we plot, we normalize, the d vector, and that's why it's a circle. Okay. So in topological phase, if you add some noise in those T1 and T2, you still remains you still get the winding number to be 1. It remains invariant. Okay. So yeah, there are other properties as well. So probably we're going to discuss this in future classes. But for now, the idea, that is that excuse me, depending on the strength of T1 and T2, we get a topological phase or the trivial phase. And we have an invariant called the winding number, how many times that circle goes around the center of the coordinate system. That's the winding number. Does it somewhat make sense? Like, or just an information, two case, topological case and trivial case. Okay. Questions? Yeah, I know it's new. I'm trying to kind of understand the theory as well. But now maybe I can quickly show you how to get the Hamiltonian so that we can try to do that some analysis later on. Um, okay, to get the Hamiltonian, I've been using this PWTK scripts, and this is the band that I got. Let me delete some of these. HR, SSH chain, MMK, and maybe SCB chain. Okay, and error one in. Okay, deleted many of the things, but I didn't delete anymore. Okay, so I have this single script, ssh.tcl, and it's in that TCL language, so it's a little different, but we set the pseudo potential name, lattice constant, this D1 and D2, they're basically separation between image cells. That's how we define T1 and T2 in this model. Remember, T1 and T2 was the interaction strength, right? So yeah, here T1 and T2 was the interaction strength between intercell atoms or intracell atoms. So here we have D1 and D2 that we just change the distance. That's how we tune those T1, T2 parameters in this case. And number of K points 16, some vacuum padding because in Quantum Espresso, they consider 3D system, but we want 1D system. So that's why we needed that. And name defined as SSH chain, output directory TMP. And if you have done a little bit of PWTK, you know that this is how we define the name list. Sometimes you can use curly braces or sometimes this quotation double quote. If we use curly brace, it's going to create the name list with exact values inside the curly brace or inside the block. But if you use quotation, you can replace with any element or any part of the block with a variable. So this prefix is going to be replaced by the name here. Okay, and we Ravis lattice 0, and we define the lattice vectors. It's a 1D system. So along X, we have the lattice vector A, right? 3.2 Armstrong, for example, along X. Along Y and Z, there's nothing. And that's why we do some padding there, meaning if they're separated by a large distance along Y and Z, then we can consider them kind of not interacting. Okay, that's why padding is kind of big, 15 compared to 3.2. Okay. And then atomic species, I'm just considering hydrogen atom, simple, because this is just a model, right? And atomic position is, their position in init cell. The first one is at 0, second one is at D1. And you need to specify the center in a 3D system. So 0, center of that box. 0 and center of that box. D1 and center of that box. It's like a 3D system. 2 atoms in a 3D cell. You need to specify their coordinate. Then this is how we run the SCF computation. Let me delete all this and run this file. So if you remember previously when we so I have this file here. When we have run the computation, I think I've shown you that if you do run PW, then that's gonna and provide a name like this, that's gonna do SCF or NSCF computation, or that's gonna run pw.x executable. And since our calculation type is SCF, it's gonna run SCF computation. So if I do pwtk ssh.tcl, this exact file, it's just going to run this computation, and it generates the SCF file exactly the way we specified, right? And it does the calculation. But with pwtk script, we want to do first the SCF, then we want to do NSCF computation. Yeah, first SCF, then we define, modify the name list for NSCF computation, calculation NSCF, and these two, no symmetry and no inversion is important, so that we have all the K points, okay? Then we're going to run the NSCF computation, and then something called Warnerization. I think I have a nice graph here. Just give me a minute. I have a flow chart that will probably give you, yeah. This flow chart is interesting. Okay, so first with SCF.in, we do SCF calculation. Then with NSCF.in, we do NSCF calculation. Then we have to have this WIN file for 1 year 90 pre-processing to generate this NNKP file that will contain necessary information for the next step, which is the interface step. It runs pw to 1year.x executable and generates this AMN, MNN, and EIG file. These are the eigenfunctions. It's just an overview. Then do final Warnerization, and we get maximally localized 1-year functions, and the output is some file name hr.dat. That's the Hamiltonian. Okay, these are the steps. Any questions? I mean, obviously there are questions, so you need to try. You can this is 5.3 2.3 for now, how to get the Hamiltonian, the flowchart. And in this PWTK or TCL script, I have written the code so that it performs the SCF, then the NSCF, then the Warnerization, and finally the pre-processing, and then the interface, and finally the Warnerization calculation to get the Hamiltonian. Okay, so if I run this, let me clear the screen. Let's give it a second. It might throw errors because my script may not be okay. So this command was problematic, but I can run it manually. and it works. If manually it works, in PWTK it doesn't. Then final command. And we have this Hamiltonian here. Okay, hr.dat, that's the Hamiltonian. So so what I'm doing with this TCL file is whenever I'm running some executable, I'm also generating the input file for that. For SCF and NSCF, if you just run this command, it generates the input file and runs the computation. But for modernization and pre-processing, it doesn't do that automatically for some reason, or I still don't know the command to do that. So I'm manually creating this WIN file, which is, where is the WIN file? Yeah, here. This WIN file, and you see these K points, they are copied from nscf.out file. This scf.out, this nscf.out. So if you go to nscf.out, you can do K point. There are 16 K points. So I just copied these numbers from there using a command to SSH chain dot WIN file here. So all the commands are here. So executing this command reads the file, and then when I create the WIN file, I can copy, use those K points and plug it in here. And then, I create PW to WN input file, which is required for this interface step. So here I have the file format, right? We have scf.in, nsf.in, silicon.win, win, and pw to wn input file for modernization, and then finally the final modernization. And this is the final command. And if you run that, we have the Hamiltonian. Now, these are the real and imaginary component of the Hamiltonian. These are the lattice vector, and all these numbers. I know it's a little complicated, but if we, I have this Python code written, and if I run this Python code get HV2, it generates me the bands. And this looks very similar to the bands we had here for, yeah, no. For trivial or topological case, the bands were like this. And here I have the bands. It looks a little different, but they're similar. The reason for this difference is that we need to tune those parameters properly. So, in QE, that's it considers things as 3D, but we need to make it 1D using those parameters, right? The paddings and like fake 3D kind of configuration so that it behaves like 1D. That's why I think those they don't exactly match, right? And yeah, that's it. That's how you get the Hamiltonian and the bands. There's a lot of things, but I have the PWTK file here. Let me show you. Yeah, I have the. Okay, what is it? Yeah, for silicon crystal, I have the SCF and SCF file, and then how to run the command, and then for honorization, silicon.win file, and then how to run the command, and then for pw2oneyear.x input file, I have the file description, run the command, and finally modernization. And there's some notes on troubleshooting, and that's for silicon. I have also written the PWTK script for this 1D system, right? exact script that you have seen here, this ssh.tcl. Okay, it's a single script. You can try to run it, and after you run that, you should have the Hamiltonian. And if you see some errors, just try to find the command that didn't execute and try to execute them manually, and you should have the Hamiltonian. And I think I might upload this way to plot the bands as well. Let me do it right away. Yeah, any questions? I mean, there you must have questions. Bands. No, this is a Python code thing. I can do begin Python and end Python. That's better. Okay, there you go. I have the Python code there as well. Yeah, I know it's a lot, so you need to try it yourself. And let's see how we analyze those properties of the Hamiltonian maybe in future sessions. Okay, any questions? Okay, let me stop sharing the screen. Um, okay, so that's all for today. You don't have to run the code for 1D system. You can run the code for any material, right? And get the Hamiltonian for that material. And one way is to say for silicon, you run the code, get the bands, and try to see the bands you get from the Hamiltonian matches with the bands you get from Quantum Espresso directly. They must match. Well, you have to keep the precision of the computations good in all the steps, but they must match. Okay. Yeah, that's all for today.
Thank you, sir.
Uh,
Assalamu alaikum.
Walaikum assalam.